So I'm going to break it up into 5 parts in this universal timeline. We're going to talk about the very early universe, which only takes place between 0 and a picosecond, a very short amount of time. That's like the building block of everything to come before. Then the early universe is when we begin to expand in the creation of subatomic particles, and pretty much the beginning. It's like the building block of the building blocks, essentially, that creates everything. Then for about 370,000 to a billion years after the Big Bang, we're going to talk about the birth of all the celestial bodies like galaxies and stars. And then we're going to briefly talk about the universe today, which is a billion years after the Big Bang towards now. And I'm going to end it with talking about the possible future and fates of the universe, trillions of years from now. So bang, that's how everything started. The Big Bang was an expansion of the universe from a singular point. That point was extremely high in temperature and density, incredibly hot. And this happened 13.8 billion years ago. This was calculated by Edwin Hubble in 1923, when he found that galaxies are moving away from Earth at a very accelerating rate, which implies that at one point, a very long time ago, that everything was very close together at one point. Nobody knows what was before this singularity, before the Big Bang. We don't know if it was there forever, if something put it there. That's when you start to talk more about, your rational religion you can get and anything like that. But it's really just speculation, because our physics breaks down before this time, because nothing really existed. So about 10 to the negative 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 78. Which is huge. That's essentially going from something half the size of a DNA molecule to 10.6 light years across, or 100 trillion kilometers. An extreme expansion. It was huge. And this expansion slowed until about 4 billion years ago, when for some reason it began to accelerate again. And nobody really knows why. That's where we start talking about dark energy, which I'll talk about a little bit later in the presentation. But as the universe expanded, temperature rapidly decreases because of increased volume, and it was more evenly distributed throughout the universe at this time. Nobody knows why this expansion happened, but it is obviously clear that it did, because it's expanding today as we speak. So 10 to the negative 43 seconds after the Big Bang is called the Planck Epoch. And at this point in time, the 4 fundamental forces of nature, gravity, electromagnetism, the weak force, and the strong force, were one unified force at this time. You can kind of think of this as like a phase transition between matter, how water at higher temperatures becomes steam and at lower temperatures becomes ice. It was so hot at this time that all the forces behaved in a way that we can't really measure or think about, because there's no way to possibly measure it. But as it slowly cooled down, the unified force split into the 4 forces that we interact with today. Now we get into the early universe. I like this background. It's kind of like the matter and antimatter I'm going to be talking about in a second. So this is another picosecond after the Big Bang is when the Quark Epoch happened. And this is immediately after the 4 fundamental forces separated. At this point in time, it was way too hot for things like protons and neutrons to form, but things like quarks and gluons were able to form.
Hey, Ryan, I do have a question for you.
Sure.
One of our guests wants to know, what exactly is an epoch, and is it simply a time period?
An epoch, yeah, it's just a synonym for an era. It's just a period of time.
Okay.
No problem. So again, at this point, it was way too hot for our basic subatomic particles to form. It was all quarks, leptons, and gluons. This is the standard model of elementary particles. You got the quarks and your electrons, muons. These are all the things that build up our bigger atoms. So at this point, the universe was very thick and opaque plasma. Think of like a foggy fire, just a bright, thick, intensely hot, chaotic place full of these subatomic particles. And about 1 second after the Big Bang, these quarks were able to form together to make protons and bigger molecules like baryons and other baryons and hadrons. Also was antimatter that was present. Now, when the subatomic particles first formed, there was an equal amount of matter and antimatter created. And antimatter is just a negatively charged counterpart of normal matter. So you have a proton in this model over here. You have a lithium atom with a proton, a neutron surrounded by 3 electrons. And an anti-lithium is just an anti-proton, anti-neutrons with 3 positrons. A positron is just a positively charged electron, and an anti-proton is a negatively charged proton. And antimatter is created anywhere where there's high energy particles colliding. And in a place like the early universe, with extremely high temperature and density, particles were colliding all over the place, trillions of times per second. But there is obviously an imbalance between normal matter and antimatter, and this is one of the biggest unsolved mysteries in all of physics. Nobody knows why this imbalance exists. About 2 minutes after the Big Bang, the temperature and pressure began to decrease, which allowed particles to fuse together. The most common one was diffusion of deuterium into helium. So this model over here, we have a deuterium atom, which is just a proton and a neutron, and a tritium atom, which is 2 neutrons and 1 proton. These are just different forms of hydrogen. And when they slam together, they form helium-5, which is very unstable. Helium is 2 protons. And because this is unstable, it shoots out a little bit of energy and boots out a neutron, which forms a more stable helium-4. And this is the building block for stars that we see today, slowly burning hydrogen and helium into heavier, denser elements. Heavy elements did form, but due to the high temperatures, they destroyed themselves very quickly. Like lithium and beryllium, they weren't around for very long due to the high temperature. Next is the cosmic microwave background. This is the earliest picture we have of the universe. This is the universe about 370,000 years after the Big Bang. So at this point, electrons were able to bond with hydrogen and helium in their outer shell. And because they're oppositely charged, electrons want to be very close to the positively charged nucleus. So in order to do that, they release energy in the form of photons or light to transition to a lower energy state closer to the nucleus. And these released photons are redshifted, which means that their wavelength is increased and their frequency is decreased over because the universe is expanding. So think of like how when a car comes by and it's really high pitched when it comes towards you and it goes really low pitched as it goes away. It's very similar to that Doppler effect except with light, where it's turning red when it comes towards you. Turning blue when it comes towards you and red when it goes away. And these released photons are redshifted over billions of years and are slowly turned into microwaves, which is where the cosmic microwave background first came from. And very interestingly, I found out that at this point in time in the universe, the temperature is about 4,000 degrees Kelvin, which means the light released from these electrons binding to hydrogen and helium were actually in the visible spectrum of light, which would make them a pale yellow color. But over billions of years, these were slowly redshifted into this picture today. And another unsolved problem with physics is how very messy this picture is. You have very dense spots of energy over here and cold spots near the middle. When an explosion happens, it's very homogeneous, very mixed well. How does it become this disorganized and heterogeneous? It's another very unsolved problem in physics that we still haven't figured out. Next is the dark age and the birth of our celestial bodies. So in dark ages, there's no light producing structures yet. There's no stars or galaxies. And the only source of photons was electrons transitioning to those lower energy levels, as I said before. But those were just very small photons that we probably couldn't even see. So at this point, the universe was 100% dark. And dark matter, which is a very, very difficult topic. It's matter that we can't see or measure in any way, but these were slowly gathering into massive filaments via gravity that interacted with each other. And this period of darkness lasted for about 300 million years. So these concentrations of dark matter pulled ordinary matter together. You can see in this picture over here, these bright spots are clusters of stars, and these big black voids are where dark matter was not. So it's dark matter that's pulling hydrogen and helium together to form stars in these little light patches here. And these dark voids are where dark matter did not congregate. So matter being mostly hydrogen gas was able to form into these stars at first. These were called population 3 stars, and they had a very, very short lifespan, only a few million years, but they would explode into supernova, and this created the heavier elements later on, such as carbon and oxygen. And galaxies form in a similar way. When the stars formed, they formed these pockets of like these stellar nurseries where many stars were forming at once, and gravity continued to pull them all together until they formed these large scale bodies of trillions of stars in these galaxies. And galaxies first formed about 500 million years after the Big Bang. It took quite a long time for it to go from that singularity to these common structures that we see throughout the universe. Now I'll talk about the universe today. So solar system formation, pretty much everything seems to form in the same way on a large scale, with these giant clouds of mostly hydrogen interacting with gravity. And it likes to form near the circle. Form near the center of the circle, most of it becoming the sun or a star. And the heavier trace elements are outside. So all the hydrogen and helium, 98% of it comes near the center and forms the sun. And as smaller clumps along the outside become planets, moons, asteroid belts, other small bodies that go around the center star. Just like our solar system, how we have the 9 planets and the sun, most of it came in the middle, and the smaller ones clumped together to form Earth, Jupiter, and all the other planets. This is actually my favorite slide, where I talk about how life formed in the universe. And this is probably my favorite scientific experiment. It's called the Miller-Urey experiment. Down here, we have a big vial of water, and inside of this, they mix together just inorganic compounds, hydrogen gas, ammonia, and methane, very common molecules found throughout the universe. And what they did was they heated this up into a vapor and sent it up this tube and into this larger ball over here. And they gave it a lot of energy with this electric spark. This was meant to simulate the Earth 4.5 billion years ago, a very violent, hot, stormy, just toxic environment. And when the water and the methane and the ammonia and the gas were given this large boost of energy, something crazy happens. After they put it through this condenser and it cooled down, similar to rain, it pulled together in this trap here at the bottom, similar to just a pond forming after rain. And after a week, the water turned black. And when observing this new liquid, they found amino acids, which are the building block of DNA and other what's the word I'm looking for? Biological molecules. This is a process called abiogenesis. And there's also a theory that nonpolar hydrocarbons, so molecules with hydrogen and carbon, could have been constructed in the very first cellular membranes in the early Earth oceans. And because this can be so easily reproduced in a lab, this probably happened on millions of planets throughout the entire universe. So life could probably be a lot more common than we think. And next is dark energy. It's called dark because it's unknown, undetectable. There's really no way to measure it that we have right now. We don't have the technology or the physics to be able to get an actual description of what this is. But this is responsible for the acceleration of the universe right now. So if you remember from the earlier slides, about 4 billion years ago, after the big rapid expansion, it was slowly decelerating. And all of a sudden, 4 billion years ago, it expanded rapidly again. And it's probably to do from this dark energy, but nobody knows where it came from and why it's all of a sudden accelerating the Earth again. And the dark energy surprisingly makes up around 69% of the entire universe. Only 5% of the universe is ordinary matter that we interact with. And the other 27% is this dark matter, which is responsible for clumping together the normal matter to create stars and galaxies and other large celestial bodies. And finally, we're going to talk about the possible fates of the universe. So first is the heat death or the big freeze. So in this situation, the universe expands indefinitely without limit. And this causes the energy to be dispersed throughout the universe. and the density will decrease until it reaches a thermodynamic equilibrium, which basically means that everything is just uniform. There's not a lot of violent reactions happening. Anything is a very equal state. If this happens, all matter will collapse into black holes, and those black holes will evaporate via Hawking radiation, which is the radiation that black holes emit through quantum fields on the event horizon. Stephen Hawking wrote a great book about that. And after this happens, all structures will decompose into subatomic particles and photons. This will take about 10 to the 1,000 years to happen, but however, life will cease after 10 to the 14 years because no more stars will be able to form. So it's called the Big Freeze because with no stars, there's no heat, and the universe just becomes a cold, dead wasteland. Next is the Big Rip, where the universe continues to expand, accelerate without limit. This causes structures formed by gravity, like galaxies and solar systems, to be violently ripped apart. Expansion eventually overpowers the electromagnetic forces, which keeps atoms together, and even atoms will be ripped apart. And if it keeps going to an extreme, forces on the Planck scale, the smallest scale that we have physical knowledge of, can no longer happen, and the literal fabric of space-time itself will be ripped apart, and everything will cease to exist. Next is the Big Crunch. This is no longer considered likely to happen, but it's still an interesting theory to think about. It's pretty much the opposite of the Big Rip, where the expansion reverses and the universe contracts back. So all matter will accelerate back to its common center, the singularity of the Big Bang, and it returns into an incredibly hot, dense state. A second part of this theory is called the Big Bounce, where this crunch might initiate another Big Bang, and the entire process repeats over and over. It could have happened a million times before, but there's no possible way of knowing. And finally, this is probably the scariest one, and I just included this because I thought it was super interesting, but the final possible fate is the vacuum instability. So in quantum field theory, there's something called a vacuum, which is a vacuum is a space with the least amount of energy possible. So the idea is the universe is not in a state where it's at minimum energy. It could be at a local minimum, which means it's low but could go lower, which means that at any possible moment, the universe could completely collapse to find a lower energy state. And if this happens, the universe becomes a more stable, true vacuum. All fundamental forces and particles in the universe will be destroyed and replaced by entirely new forces and structures. And due to the quantum mechanics and the nature of vacuums, this could happen at literally any second. So if you want a little bit of an existential crisis, there you go. And I think that's the last slide. Yep, that concludes my presentation.